This is Carl Freund with Cambrian-AI Research, and today I have some researchers from IBM Research that are focused on quantum computing. Not so much the machine we've all marveled at when we've seen pictures of the IBM Quantum, but how to use it. And they're talking about something called Quantum Serverless. Ismael Ferro, who's a researcher in IBM Cloud and Quantum, and Blake Johnson, who's the lead in the Quantum platform. Welcome, gentlemen.
Thank you.
Great to have you. Great to have you. Why don't we start at a high level and just explain to the audience what's the state of quantum? It's sort of like almost always there, but not quite there. What's going on in the world of quantum, and then we can dive deeper into your specific area of research.
Sure. I mean, quantum computing technology has been on a remarkable journey. It's kind of emerged from being a laboratory experiment that someone needed to be a PhD to be able to construct, 1 or 2 qubits to something that really is now accessible for a lot of people to explore with and experiment with. From people still learning about quantum computing and quantum mechanics to people that are investigating early ideas about how we can actually use this technology to solve problems in application domains and things like chemistry, machine learning, finance, and so on. And that's enabled by the fact that these systems are now accessible and increasingly powerful, right? Like IBM Quantum today has 23 quantum systems available through our IBM Quantum portal, and also directly integrated into IBM Cloud accounts. And those systems have increasing performance, both in terms of scale, the number of qubits, the quality or the quantum volume of those systems, and the speed with which those systems can execute quantum circuits, something we measure with something called CLOPS. And so all of those performance metrics are continuing to improve, which makes it possible to explore a greater variety of workloads that you can execute on these quantum systems.
And I take it that the state of the art has kind of shifted from, can I make this thing work, to how would I use it in a real environment? And to do so typically requires a heterogeneous approach, correct? Where you're using CPUs or accelerators in quantum.
I mean, that's right. We don't view quantum computing as a technology that sort of works in isolation, right? It works in concert or with other kinds of computing technologies. And so we view our task really as how to allow the user to express the quantum and classical computing mixture that's appropriate for their task at hand. Maybe Ismael wants to say more about that.
Yeah, I think that at the end is like in machine learning field, you can see that at the end you combine CPUs and GPUs, no? Each of them for different elements or different parts of the computation. We believe that the quantum computer are going to be other element more. No?
Mm-hmm. So when we first talked about doing this interview, you mentioned quantum serverless. Can you explain what you mean by that term?
Yeah, I can take the beginning of that. Yeah, for us, the quantum serverless is another abstraction layer in all the software stack that we are building. We start 6 years ago to facilitate access to our quantum computers via cloud. After that, we create a SDK that allow to the people, some kind of developers, no, that we call kernel developers, to facilitate to write the quantum assembler that you can execute in these quantum machines. And after that, we continue to add more layers of abstraction to simplify how the people can use these quantum computers. Quantum serverless for us is the element that allows to our users to combine classical and quantum computation and in a simple way, without to need to pay attention in all the elements, all the technical details behind the scenes, no? Like network, like classical and quantum resources. The idea is how we can bring some kind of layer on the top that facilitate to our algorithm developers, people that want to create algorithms and solve problems, how facilitate some kind of layer libraries that allow to these people to take these big problems and in our case, slide these problems, no, or create or separate the problems in different small parts and execute part of these problems in classical computers and others in quantum computers all together. No, that is part of our serverless idea.
Interesting. So not quite democratization of quantum, but at least making it more accessible for more problems. What kind of problems are you seeing people experiment with this quantum serverless? What kind of problems are people trying to address?
I mean, there's a number of different domains that we're excited about deploying this kind of technique for different, and they basically describe different ways of partitioning a problem into a classical and quantum part. There are approaches that partition it kind of at the problem description itself. So you can think of a chemistry problem where you want to define like the ground state energy of a molecule, or maybe you want to calculate some of its other properties like its emission spectrum and so on. And you can think of addressing that problem directly trying to partition it in the problem description. So like in the chemical world, you have kind of the bound electrons or the in filled orbitals, and you have free electrons in the outer shells. And you can, one way to partition such a problem is to use kind of classical techniques to describe the core using like density functional theory methods, which quantum chemists have developed over the past 6 years. Which are methods that can work in our classical technologies, but are making approximations, right? That's what allows them to work. And so they have certain inaccuracies. And maybe you can boost the accuracy of your chemistry simulation by using the quantum computer to then just to simulate the outer shells, the kind of the free space of the molecule. So this is kind of a method that kind of stitches together quantum and classical computation in the problem description. I'm going to partition some part of the problem to treat with a quantum computer and some part to treat with a classical computer. There's other approaches that are kind of blind to the problem description itself, right? In some ways, a lot of our job building these quantum systems is a user sends us a quantum circuit that they want us to execute, or a collection of quantum circuits that they want us to execute. And we really have no idea what problem they're trying to solve, right? It's a bunch of quantum instructions that to go execute. And we can also take this concept and try to use it to be able to execute larger quantum circuits, because we can cut those quantum circuits either in sort of the time domain or the space domain. So we can cut it sort of vertically or horizontally. I'm talking about cutting a mathematical object, right? I'm not actually cutting physical wires. And I can, there are ways that you can basically cut your circuit apart and execute those separate parts, and then use classical post-processing to emulate the effect of running the larger circuit. This is kind of called circuit cutting. So like these, we believe that there exists a sort of a collection of problems that are addressable with various kind of circuit knitting ideas, right? Various ways to separate your problem into parts that you're going to execute quantumly and parts that execute quantum classically, and then to knit or with post-processing, bring those computations back together to be able to address larger problems with more accuracy.
Interesting. So what challenges do you see lay ahead? Last time we talked, you mentioned this is a multi-year journey to actually produce something that would be widely applicable. What challenges are you working on that you're especially excited about tackling?
The first, obviously, is the hardware itself, the quantum hardware, because we need to continue. We have a clear roadmap that are going to take time, because at the end, we need to understand that most of our elements continues to be under research. But taking that in consideration is and taking consideration that we have a clear roadmap about the hardware. The other big challenge is the software itself. No, like Blake mentioned, it is like not only from the potential problems that there are in this moment, like chemistry problems or machine learning problems that we can see where we can put some kind of quantum computation plus classical computation to address the problem. Also discovering new ways, to try to accelerate or solve the problems taking in consideration more the foundation of the quantum mechanics. That is other huge problem that we need to address. And obviously in the middle, how we can stitch all of this hardware and theory with software that allow to the people to have access to this quantum computation in easy way, no? To try to make more understanding, is like try to simplify how the people can use the quantum computation itself. Quantum serverless is one of the points that we want to continue to explore and put in front of the users.
Yeah, let me come back to the quantum services comment in just a moment. But first, perhaps you can share just a few milestones we can expect to see along the way as you make progress.
I mean, at various different points, we're going to be producing prototypes, candidate solutions to this problem. And already later this year, we hope to show off sort of our latest prototype of this concept of, sort of developer tooling that allows users to explore quantum serverless. We did another similar demo last year at our Quantum Summit for a prototype that was built off of IBM Code Engine. And I think this year we're looking at being able to extend what we learned from building that prototype to something which is deployable on a broader variety of classical hardware, whether it's on premises clusters or other clouds, but make something which is more portable.
Interesting. So let's get back to the question about how you expose these services to the users. How do you expose that quantum resource to traditional developers who may not be experts in quantum, understand it well enough to posit the theory that, hey, if I could use quantum here, I think it would help me tremendously. How do you expose those quantum resources?
Yeah, for the moment, we try to create this infrastructure related with how facilitate through the cloud bring access to the quantum computing. And obviously, this is access to the hardware, but on top of that, all the software that we were working for the last 6 years was focusing first, teaching the people how to use the quantum computing, okay, from the low level part, and now continues to add these new layers, no, and facilitate libraries and tools and learning tools to understand how work the quantum computation and how take advantage of that, and now in this moment how combine with classical computation, like Blake mentioned, to make this circuit knitting and circuit cutting methods. And on top of that, we need to continue to, for the next years, to continue to add more layers on the top to be sure that at the end we are going to have a set of tools that facilitate the understanding about how we integrate quantum computation in classical applications. This means nowadays all of the applications that you can see around the world is classical, no? It's everything happening in zeros and ones, and the idea is how we every time we add more elements, more libraries that facilitate at the end to have better integration between this classical application and the quantum application. For that reason, we're working now in the quantum serverless, but in the future, the next layers of the application, like we need to put focusing some kind of a specific application areas like machine learning, chemistry, and others. But again, it's to try to continue to create some layers that abstract all the complexity behind the scenes and facilitate the tools to the users to integrate in classical applications.
And these layers are...
Yeah, go ahead.
If I could jump in here, these layers are really critical, not just from like making it accessible to the user, but also making the technology work, right? Like there's one of the challenges you asked about before is sort of the different timescales of computation, whether it's like real-time interaction of sort of dynamic circuits, feed forward feedback of quantum measurements, to wanting to potentially make a hop between clouds to access some sort of specialized classical resource, and so. Like these layers need to sort of express broader, like larger and larger chunks of work so that all the timescales work. And one of the critical sort of developing, one of the critical technologies that we've developed just recently is the Qiskit runtime, which allows us to express some mixtures already of quantum and classical computations. And we've used that to start to build up these layers of abstractions. So we now have these Qiskit runtime primitives, which allow you to do more. Instead of just say like, execute this circuit, I can ask questions about those circuits. Like, I want to estimate some quantity, which is related to the output of this circuit. And I'm going to do that by running mini circuits. And so like this both solves the user need of wanting to be able to talk about slightly more abstract things. And it solves the technological need of having sort of enough work to do that the timescales all sort of work out. And you can contemplate these different kinds of computing resources working together.
And I think the watchers of this video can learn more about Qiskit at your website. I went on there the other day and learned quite a bit. Well, from my perspective, I learned a lot, a lot more that I don't understand, but it's fascinating. You can use this runtime to help stitch these together, and that's very interesting. Is there anything else you'd like to comment on? Perhaps the intersection between quantum serverless and high performance computing that you find interesting?
Yeah, connected with the last comments from Blake, that is one of the areas that for us also is so important. No? This HPC space where from a lot of years, a lot of institutions and companies try to pay attention in how have a huge classical computation in a distributed way. It's something that at the end is one element that is very, very similar to the things that we try to do in quantum computation. This means like we need to address huge computation, okay? Taking consideration some limitations about the timing, that at the end is latency, the memory sharing, a lot of things that at the end, if you try to create some kind of computation model that facilitates you to simulate big simulations, like again chemistry or weather simulations or other big simulations. It's possible that these HPC solutions, again, from a while, all the people that is working in HPC have a lot of expertise in these specific fields. And we believe that our quantum computers need to take a big role in that scenario. And in fact, this year we present this idea about this quantum-centric supercomputing, because at the end, if you see in the last decades or the last years, you can saw the evolution between CPUs centric supercomputers. That was the first supercomputers. After that, in the machine learning era, you can see that all the things moving around about the GPUs, no, this AI centric supercomputing, and we believe that now we can add in some moment in the future the value of the quantum computation there, and I think that is where the quantum computers are going to reflect or demonstrate what is the quantum advantage in combination with all these CPUs and GPUs all together in these scenarios where the HPC in this moment have the control or is the leader in this kind of computation.
Interesting, very interesting. Well, gentlemen, thank you very much for your time today. We'll be watching with great interest as you continue to develop on this path of quantum serverless. So thank you guys very much, and take care. Have a good week.
Thank you for the invitation.
Thank you. Bye-bye.
Bye. Take care.